After this talk, there will be the opportunity to ask questions to our speaker. If you have questions, please do submit them also throughout the talk if you want, throughout the talk in the chat. And I will then collate the questions and ask them directly following the presentation. And I'm very, very delighted to introduce our speaker today. This is Dr. Cristina Rodriguez Rivero, and she works in the Department of Engineering in fluid dynamics. And her PhD was in the design and process to manufacture soft matter microcapsules by using liquid jet instabilities. I asked already a lot of questions about this because I got quite interested. After finishing her PhD, she worked on the understanding of liquid drops and liquid jet behavior in digital manufacturing technologies, so state-of-the-art stuff. She extensively collaborates with companies to improve and optimize dispensing techniques. And Cristina Rodriguez Rivero is super involved in outreach and participates in science podcasts, STEM ambassador activities, science story writing, and is also our co-convener. So super engaged and always interesting to talk to. And I'm glad to have her here today. Welcome, Cristina. And the room is yours.
Thank you, Eva. It's just such a great pleasure to have you as a host. Lovely person. Okay, let me just share my screen without further ado, especially because I think I'm going to be talking quite a lot. I hope you can see it. A couple of things. If you have like any kind of burning comment or questions while during the talk, I'm happy to take them. Otherwise, again, we'll go to the end. And yeah, and Eva, if there's something not working, just let me know. It's fine. Just unmute and tell me. Okay, so basically the idea of this talk is mostly giving you an overview on how fluids behave and why that is very complex, but also why they are really beautiful and a couple of other things. So just to warn you, this is not the typical talk that I would give to my research group, let's say. So it's not about this is my research line and I'm going to tell you about it. I'll say some on the research lines I'm working on, but quite at the end. So basically, because this is getting broader than I thought at the beginning, I should have gone for changing the title slightly. So it should be the mechanics of fluids. So you'll see why in a second. So, okay, this was again very broad. I didn't know how to put everything together. So I went for starting with some concepts and a bit of the history of mechanics and fluid mechanics in parallel. And then a couple more things that I will be explaining later. So let's start with some concepts. So what is a fluid, or when did we start somehow distinguishing this state of matter? So, okay, so if we come back to the ancient Greeks, and of course before that, but in the ancient Greece, we know that they were already playing around with things like water, oil, steam, or air. And they noticed that these were different to some other states of matter, like solids. So they basically realized that the particles have extreme mobility and that they separate from the bulk in a different way. But they also saw differences among these materials. So air is different to water. They saw that sort of compressibility of the air, and then some other correlations of temperature, volumes, and pressures. Okay, so then in Greece, I have to just talk about the 4 properties of matter, or the classical elements put in the words of Aristotle, more or less. So when a philosopher, or their philosophy, was kind of the same as natural science, it was called natural philosophy. So we have 4 properties of matter: earth, water, air, and fire. So of course you can see there how important fluids were even at the time. Mechanics, so that's basically the motion of physical objects. So let's get into this. I would like to talk about the history of mechanics, how it developed and how it developed in parallel with fluids. So again, this is also an excuse to mention a couple of scientists I really admire. So I will leave them there on the slides. I may not mention all of them. But okay, let's go. So to start with, of course, Mesopotamians and Egyptians knew how to go in rivers, build bridges. So they also had a bit of a knowledge of fluids. They interacted with them, of course, but they didn't seem to leave any sort of writings describing what they had found out. So we have to go to Aristotle, as I mentioned. So he started doing experiments, or what we now these days call experiments. And then we jump to Archimedes a bit later. We consider him the father of statics. So that is when bodies are not moving, basically. And you may know him especially because of buoyancy. So again, he did quite a lot of things on fluid mechanics. And then we have a great engineer of the time, Hieron of Alexandria. Also did pretty cool stuff with steam mostly. Okay, so then we jump, of course, you know, Dark Ages and all that. So we have to jump to almost Galileo, or around Galileo. We're going to jump there. So Galileo started the scientific revolution, or what we call these days scientific revolution. So again, he brought back some principles by Aristotle or Archimedes. He started doing more experiments, mechanics. And that sort of scientific revolution we consider finishes with the Principia Mathematica of Newton. So Galileo did a lot of things, but again, he worked also intensely with fluids, and he did quite a lot of things on floatability, for instance. Then we have Kepler. We have Newton. So you know Newton for many things, but I don't know if you knew that he started or established the basic principles of viscosity. So we have something that I'll talk about later, which is called Newtonian fluids. And then I'll be talking about Euler, Lagrange may mention him, but they are more in the mathematical side of things. And of course, I didn't want to forget some of the big ones too. So Leonardo da Vinci, you may think that again, he did a lot, or he observed a lot of things in fluids, but maybe he didn't get to any laws. That's not true. He basically got to the continuity equation in a very simple way. But basically, it's basically saying that the amount of fluid into a surface must be equal to the amount of fluid out of a surface. So we can consider him one of the father of fluid mechanics, actually, because of that. Then I'll talk a bit more about Bernoulli, Euler, or Stokes a bit later. And a bit of a digression, but I wanted to say this just because Einstein, for instance, you may have heard that he did work on Brownian motion. Actually, his PhD thesis was about fluids, and he got to a relation in between shear viscosity, we'll see a bit more about that later, and the diffusion coefficient for low concentration dilutions. There's an equation, a Stokes-Einstein equation. And actually for general relativity, there are some solutions that are based they're called fluid solutions because they are based in fluid principles. Okay, so after the history, I would like to then mention what sort of branches developed from all that research. In fluid mechanics. So we have kinematics, so that's basically the study of the motion of particles, but we don't care about the causes. Then we have statics, so that's the equilibrium of things, but there we want to know why, so we want to also study the forces. Then dynamics are basically the effect of those forces on motion of liquids, for instance, or solids. Particles. If we go for fluids, we can distinguish, of course, the big two fluids, water and air. So that means that we can start combining those concepts in hydromechanics or aeromechanics, hydrodynamics, aerodynamics. And then we have some of things such as hydraulics or experimental hydrodynamics or mechanics of flight or aeronautics. So all of them distinguishing different things. Okay, so I'll be mentioning some examples in which fluids are around us, but let's start big. So we can say, see currents, we know like atmospheric relations and climate, but we can also take that to other planets. So again, we were talking about cosmology with Einstein, but also planetary science. So that's very big. But then if we come a bit closer, we have things like birds flying, the spread of seeds, the behavior of water on plants, rain, etc. And we are great at imitating nature and observing nature. So again, we've imitated birds. We've gone for imitating, I don't know, blood circulation and all that with pipes, controlling flows. And also we've done a lot of manufacturing techniques based on fluids, such as those that I mentioned there. Okay, so after, I hope you're kind of convinced of how important it was and it is for the history of science to study fluids. I want to also try and convince you why we should be using it a bit more intensely in educating, I would say, in primary and secondary school. So to study fluids, you need to understand what pressure is and some of their properties, of course, mass and volume, and also the effect of forces, energy balances. So I think that opens the door to a lot of physics and engineering fields. And then, but not only that, what I like the most about fluids, it's basically how some behaviors are very counterintuitive, and there are many paradoxes when you study them. And I think that opens, again, the room for out-of-the-box thinking and creativity. So I don't want to go into the details of all of these, but there is one paradox that I would love you to check a bit more on. So basically, okay. So basically, there is this paradox called the hydrostatic paradox, and as I mentioned there from a paper, it states the fact that in different shaped containers with the same base area, which are filled with a liquid of the same height, the applied force by the liquid on the base of each container is exactly the same. So that's something that Pascal already knew. However, if the shape of the container is different, the amount of the liquid and as a consequence, the weight can greatly vary. So there's a bit of a paradox in between kind of that pressure, like the force that you're applying at the bottom of the container, and the weight of the whole system, and what a scale is going to measure somehow. Again, Pascal, father of hydraulics, more or less. And this gets even a bit more interesting. So this paradox, actually. So we have Descartes. So Descartes' approach to hydrostatic is shown to be quite different from that of his contemporaries. Above all, in its attempt to provide a natural philosophical grounding for hydrostatics, while at the same time using it to develop a range of concepts, approaches, and ways of thinking through problems that would shape Descartes' major work in optics and cosmology. So again, as I said, I think it makes you think quite out of the box and be very creative. I'm going to mention briefly here, because that links with the next section, the Bernoulli's principle. So some people find this very counterintuitive, and maybe this is because I've worked with it for some years now, and it may be rooted already in my brain, but I get the point of why some people may find it a bit counterintuitive. So it basically said, like, within a streamline, so that's basically what just imagine the picture I have there. It's pipe, and then the gray line is kind of water, like following the flow. So within that streamline, and let's consider horizontal flow, points of higher fluid speed will have less pressure than points of slower fluid speed. So some people say, well, when you have the liquid in that contraction, the velocity of the liquid just increases. So that feels a bit like it pushes more, right? So it has more pressure, but that can't really be it, right? Because we need to balance the energy. So the energy in point 1 has to be the same as the energy in point 2. So if you have, let's not consider again the height of the fluid. If you have like a higher kinetic energy in point 2, to compensate with the left-hand side of that equation there, you need to kind of decrease that kind of internal energy of the fluid, right? And again, this is a very, very important principle. And there are a couple more things that not only the applications, but I find very interesting the role of the assumptions. So it's something that in physics and engineering, people do quite a lot. So we have to consider every time we go for solving a problem, whether, you know, like if the flow fulfills certain criteria. So in this case, we're talking about an isentropic, inviscid, that is non-viscous, incompressible, irrotational, infinite, steady flow, so that fulfills the equation, and also subjected to conservative forces. So again, this is an interesting way of looking at it too. And then applications, you can see them there, loads of them. And there is a bit of a controversy about the lift force. Yeah, so it's great. This is another one, the justice cap of Pythagoras. So basically, very quickly, if you fill the cap up to, let's say, just below that U shape that you see in the second picture, that's fine. You can just like have your water there and drink from the cup. But then if you go above that level, then it just suddenly starts dripping out and all the content just goes. So that's basically sometimes called the greedy cup. And basically, this is also known as a Bell siphon, and it's in your washing machines. Basically, that's what happens when in your conditioner bucket. So things are not easy to explain sometimes. So you may have thought about this before. So a siphon, generally this happens, or this effect happens when there is flow like uphill against gravity, and that is kind of maintained. So some people may say, okay, you know, this is a typical explanation. So, you know, gravity pulls the liquid. So then on top of the siphon, that tube that you see there, there is reduced pressure. So that means that the pressure, atmospheric pressure on the upper container pushes the liquid to compensate that pressure difference, and just that, you know, makes it just go to the other side. But what happens if I tell you that they operate in vacuum and that height exceeds the barometric height of the liquid? And some of you may understand what I mean with barometric height, but that means that it can't be pressure difference then. So then there was, and this has been discussed for centuries, there is a second theory, which is basically it's due to cohesive forces. And actually, it depends on the situation. It can be both things. So yeah, so that's really interesting. You may think, where do we use this? Again, in this particular case, it's for a health device. So you see there, like how you need to understand characteristics of the flow. I just want to briefly mention cohesive forces. So these are the ones, for instance, responsible for plants just moving nutrients upwards. So you may have heard about capillarity. So that's basically due to both surface tension and adhesive forces. I won't go into the detail, but those cohesive forces also make some quite nice effects you may see very often. So there are some Marangoni flows, that's basically flows due to surface tension gradients between different liquids, or with a solid in contact with a solid. So there are things like the wine tears, or the lovely effects in bubbles, so bubbles. So yeah, there are many kind of special issues, many papers on talking about teaching and learning with fluid mechanics. And there are a lot of fancy things about, you know, atypical experiments, you know, the paradoxes. It's just like, it's really cool to see. And again, I didn't have it in secondary school. I would say I would have loved to. Luckily then in university, you use it in many degrees. But yeah, secondary school should be somewhere there. Okay, so let's go to some math a bit quickly though. So just the approach of this. What I want you to kind of have in mind is that the motion of a fluid is not the same as the motion of a solid, but in the sense like if you consider a translational motion, for instance, if you get a block of solid, all the points in the solid will be moving at the same speed. However, if you have a liquid, that may not be happening. So that translational motion will be different for different points in the liquid. So that's an issue, and we'll see why. So basically what we tend to do, I think it's more like, okay, just get your model, whatever you're going to design or experiment or whatever, and then apply fundamental physical principles. So that's conservation of mass, conservation of momentum, and potentially conservation of energy. And then maybe you'll be lucky and you can extract exact mathematical expressions if you're lucky. Why? Okay, this is a sort of thing we may find going for, again, let's start like relatively simple. So this is from an idea like Newton's conservation of momentum. Euler just started trying to define the different forces and study different forces on a small volume of liquid. So I'm going to briefly mention things like normal stress or shear stress or gravitational forces, right? Euler went for developing something simpler. So he said, okay, I'm not going to consider viscosity. So that means shear stresses are 0. And then the normal stresses will be just pressure and then gravitational force. And then he got to this expression here, which is lovely, beautiful, but again, it's a bit complex. We start having partial differential equations. We have things that depend on time, like velocity, but also depend on space. So things start getting a bit complicated. Then Stokes and Napier in France, Stokes here in Cambridge, actually, they extended that to consider viscosity. So that means now the normal stresses are a bit different and shear stresses are coming to play. So this is a similar expression as we saw before. Like we have also like a pressure component. We have some body forces, that's kind of the gravity. It could be more things like electrical forces and so on. And then we have a more complex bit of the equation to define the viscosity, basically, or kind of that sort of relationship that I will mention in a bit. Pressure and viscosity, those are considered surface forces for the things we saw before. And again, you can just like, this can get a bit simpler. For instance, if you have like a constant density and a constant viscosity fluid, then that means that, you know, this reduces to that expression there. If we go to energy, again, this gets quite mad. You have way more things to consider. And there are more ingredients to it. You have to use boundary conditions, which again, it actually helps you in sorting things out. And then there's viscosity, as I was mentioning. What is viscosity? Basically, it's what defines the resistance of a fluid to flow, basically. And it's defined as the ratio of stress to the rate of strain. So a Newtonian fluid, I don't know if, I hope you can see my mouse. So a Newtonian fluid, basically, that relationship is linear. But so that means that the viscosity is basically constant for all shear rates. However, it could happen that that relationship is not linear, so your viscosity depends on the shear rate, like these situations, and things start getting complicated. So this is basically some studies that I did during my PhD, characterizing alginate, different solutions of alginate. So you have then different types of ways of characterizing the flows depending on what you need. I needed a couple of things. So I did several studies, but you have, you know, shear flow, extensional flow, etc. And I did that because basically I was studying an instability described by Lord Rayleigh, who was also here in Cambridge. And basically, the instability is about how jet of liquids break into droplets. So what I wanted was basically finding the optimal conditions of the perturbation, because I was imposing like a mechanical perturbation. So what sort of perturbation I needed to apply so that I would have a lovely breakup with no strange kind kind of small droplets in the middle, or, you know, kind of the sort of size that I wanted. Basically, I wanted to encapsulate some proteins. So this technique is not harmful for protein encapsulation and other biomolecules. So basically, I started with things like, okay, this is kind of the perturbation I'm going to apply, and that means that it's also affecting some fields like the velocity fields or the tension and shear rate and all that. So I linearized those, the analysis, and I got to a dispersion relation. That was my goal, basically. So how I did that a bit quickly, as I mentioned before, continuity equation, and then Navier-Stokes, and then applying a particular model for that strange relationship in between stress and shear rate. And then I got to this dispersion relation after some math. And you can see here, this OH or this EL, these are dimensionless numbers. So I'll mention in a bit what those are. So basically that relation just allowed me to tune in parameters and just have some curves which would tell me which frequency I should apply to have like the best instability somehow. Okay, so useful things we can do to solve those sort of things. As I was mentioning before, scaling we do this through dimensionless numbers. So that means that using certain numbers as the one that we see there, which is very, very important, the Reynolds number is called, we can get to situations in which the Navier-Stokes equations are invariant as long as you keep those parameters, like that ratio, fixed. So that means that you can conduct experiments in smaller scale prototypes or bigger scale prototypes. It depends like what you need. So after that, Reynolds give you more information. When the Reynolds number is small, the equation that we saw before is mathematically nice or not too bad, and you can linearize things. That's the equation. But when the Reynolds number is large, the non-linearities of the equation are are more important, and then it gets very difficult to solve. And it happens because of kind of a simultaneous spectrum of scales, again, as I mentioned before, in space and time. So it gets really complicated. And there is something called turbulence. So this is kind of the big monster of fluid mechanics. So there are some things that we understand. There are some patterns like that one that you see there. But in general, again, I've had this many, many times, defining our understanding of turbulence as ad hoc and limited. So there is something that I like to, that I always like to tell people about turbulence, and this is attributed to Heisenberg, but it's probably not true. But I mean, apparently, yeah, many, many big scientists have said similar things. So this is like, when I meet God, I'm going to ask him 2 questions: why relativity and why turbulence? And I really believe he'll have an answer for the first. So again, you can have a feeling of how difficult it can get. Yeah, I kind of find very interesting how people just put that in the news. I'm going to check the time because probably, yeah. So what can we do then? Okay, using analytical and mathematical techniques, various of them. Thanks, mathematicians. I'm terrible at this, so plenty of things of work down that route, and also numerical and computational techniques. This is more like PC-based computational fluid dynamics. Won't go into the details, but you also need experiments. That's the fun. I'm more of an experimentalist, you may see. So there are main features of experiments. You have a lot of scales. As I mentioned before, you can also do a scaling, so a bit of everything, or you can go and do like, field research and go to the ocean or whatever you need. Then there's a lot of laboratory setups and a lot of data analysis techniques. So these are a couple of examples. So particle visualization, the big technique. You can apply a lot of things there, but again, it's about seeing somehow how the fluid around certain bodies behave, or things like those. You can use materials deposited on surfaces, and then again, optical methods that link generally to that particle visualization. You have to characterize the liquids, basically, or the gases. I'm mostly going to be talking about liquids, really. So this means characterizing the density, the viscosity, and the surface tension, mostly. But then you also have things like the speed of sound in the different media, or also the compressibility of that fluid. And I'm not going to go into the details, but you know, there are a lot of techniques. They get better with time, but those are kind of based on similar principles generally, like for viscosity, density. But there are some things also that comes like really fancy techniques, new techniques. And in this case, it's about a tensile strength with an optofluidic chip. So there are very exciting things out there. So, okay, so let's jump to Inject. Because I want to talk again a bit about what I do. So basically in small scales, so let's go now planetary systems, but something smaller. So we have this sort of kind of microfluidic devices, and we also have some other phenomena happening kind of more, you know, in kind of open atmosphere, let's say, which are called like free surface flows. So basically I work mostly with free surface flows. And again, as I mentioned before, we know how to imitate the nature very well. And we need to understand how things work to try and do it even better. So we have here like agricultural aerosols, or again, printing, 3D printing, 2D printing. Okay, so Inject Printing is basically a digital and non-contact transfer of liquid drops into specific locations on a substrate. It tends to be a solid substrate. Why digital? Is basically because you have an image, for instance, and that lives in your PC, and then you can change that as much as you want, and then you can send that information to your printing device, and you can just be continuously changing it. So these techniques deal with droplets from about kind of 10 micrometers to something like a millimeter, depends on the technique. And you can see kind of these scales basically. So 10 micrometers is about the diameter of a red blood cell. And then you have things more like bigger, like kind of the diameter of a piercing needle. Okay, I work mostly in kind of those ranges, 30 to 100 microns perhaps. Okay, so it is very useful, as I was mentioning, when you have to change the information from product to product, so coding and labeling, for instance. And also in things like that. So you can, when you go home and check in your fridge, that's done with a technique called continuous inject printing. So basically, the principle relies on Rayleigh instability, again, as I mentioned before, during my PhD, and then electric induction. So it's really a great technique to combine a lot of things there. So, okay, so I work mostly with drop on demand, and that means mostly piezoelectric and thermal inject printing. So thermal is what you find, I don't know why it's doing this thing, probably had its whatever. So thermal is what you find at home generally in your printer, and it has the ink and the nozzles in the same kind of device. And then there are more industrial devices in which generally you can recirculate different types of inks. So again, it's compatible with more applications. I use those sort of devices generally for research. And then again, with that, you can stack different print heads as in the printer at home. And then you can work out kind of how to combine different colors and different drop sizes to get different parameters. Okay, so this is basically my hand and a small printing device with a single nozzle. So it's basically a capillary. Sorry, I didn't put the scales, but that's about 120 microns. So that's probably, I guess, about, let's say, 80 micron drop. So basically it works by squeezing a capillary glass, in that particular case, with a piezoelectric device. So we need to, the input would be electrical. So this works as an open microfluidic system. The energy for ejection, you get it again from that waveform I was mentioning, so electrical. So what we have is basically electrical energy to mechanical from a in a piezoelectric device to acoustical inside a chamber with liquid, and then fluid dynamical when the liquid leaves that chamber, because it's basically the chamber is squeezed. Lots of acoustics going on again inside that printing device, and then more surface tension around, mostly around the area where it's dripping. It's not considered dripping, but when it's ejecting. And then more things, droplet formation, next stage. So you have to consider, of course, the characteristics of the liquids, and then also some other things happening during the evolution of that flight. So airflows, thermocapillary motion, electric charges, etc. So, and again, this is a balance of energy, kinetic, surface energy, and viscosity. You have to play with those. The goal, making the drops to land where you want. So being accurate and also having the coverage on the substrate that you need. So you want to generally maximize the loading of that ink with solid, for instance, but there are some limitations. You don't want to clog your nozzles. Viscosity and surface tension are limited. And then again, once the drops land, you have a balance, again, kinetic energy, surface tension, viscous dissipation, and that defines your spreading and penetration in the liquid, in the solid. So, sorry, like it could be paper, it could be. So the ink, a lot of things to consider there. It's not only the printhead performance, it's about storage and how it then stays in the media for a long time. And they have things about the integration. They could be, if you pile up more nozzles, there could be, electrical crosstalk with those piezoelectric devices, mechanical, and also fluidic within the flight of the drops. And then you have more things, dissolved gases, and then you need feedback control, and of course more things about the bigger elements in a printer, right? It could be the feeding system for your substrate and so on. So this is me being very serious in the lab. So what I like is basically research on the evolution and the flight of the droplets. So there are quick things. I did some research with a company here based in Cambridge, and they basically had the problem in continuous inkjet printing of having certain conditions in which they would see some ink or some deposits of ink being deposited in one of their electrodes. So basically what we did was going for some particle visualization with a scatter light from a laser, and we checked again the nature of those deposits with SEM and also Fourier transfer infrared spectroscopy. So again, you can see how we need to characterize many things in the process, and then basically did some particle tracking with that laser scattering I was mentioning. Those are stacks of the images we got. And we studied how the drop behavior changes with the modulating voltage. The modulating voltage is actually what I was kind of calculated in my PhD for, again, a similar technique, and some of the voltages involved in the process. So there are things like you get the trajectories, you also work out the velocity, so that's position against time. Balance of forces, in this case is way simpler than in other cases, but basically we were just studying basically because that was the other forces were negligible, electric force and drag on the particles, and basically that would give us a charge to radius to start with. If there's someone working with mass spectrometry, they may say that charge to radius is not what they tend to report. It's more like charge to mass. So we'll go for that in a minute. So doing those calculations, considering the initial, or the final weight of the deposit, we can get a charge for those droplets, we can compare that with the droplets that you deviate because you want to deviate, not those ones that you're not wanting to deviate and somehow it happens. And we just concluded that there are some systematic charging that needs to be further investigated. And actually, yeah, in this particular case, the second way of looking at it was basically kinematics. So I don't care about the forces, I just care about the trajectories. The first case was more about forces and more dynamics. And then there are some other things pretty quickly. Understanding printing effects, such as that you can see there. It starts like we have a printed pattern, it starts very nicely, no strange defects or strange patterns. And then suddenly we get that pattern that we tend to call wood graining because it feels like wood. We don't want them, but you know, they are there. And this is what happens. I'm not sure. Oh yeah, it runs. So you have, yeah, so that happens. You saw an image of this before, I think, when I was talking about turbulence. So great, the fun is there. So we need to study what's going on there. So basically, again, we need to consider here things like an entrained flow of a type Couette, if someone knows of those flows, between parallel or non-parallel plates, depending on how your substrate is, and then boundary layer effects, flow disruption, wakes, so cross flows in general. So again, doing some particle image velocimetry, you can get velocity fields and vorticity fields, as in this case down here at the right. So very interesting to then compare with your theory. Some of the challenges, what happens if your addition is terrible? Then you have to work out how you have to drive the inks and all that. Integration, robotic arms, functionality, you want them to be conductive. Are they as conductive as you want them? And I want to finish with something like really pretty that I heard not long ago. I was just Dept was organizing a seminar on George Bachelor. So he was studying turbulence here in Cambridge. And he has this lovely work about research as a lifestyle. And there are things like scientists and engineers engaging in intensive research, lead uncommon and many would say strange lives. So sometimes I think many of us could feel the same way. There are things again like talking about fluid mechanics, like the fluid mechanics community. I believe that the understanding, trust, and goodwill between members of this scientific community transcends geographical and political boundaries and constitutes one of the most important forces for international harmony and friendship in the world today. I think it's a lovely community, actually. I think this may happen with some other things, but not with many communities, I think. So I want to leave it there. Thank you very much. You can find me in the Institute for Manufacturing, and I would love to get feedback and questions and all that. And I'll be sharing more things, but back to Eva.
Thank you so much. This was really interesting, and it's kind of probably different from what I thought it was. Do we have any questions? Otherwise, I will have some, you know. Oh, there's one. Does location on the Earth alter the effects of inject printing? That's what Stephen asks.
No, it does not, especially because most of the gravitational effects at that scale are very low. So it would affect, again, in some sort of gravitational field stronger than the one we have on Earth. Here, it's those effects are very, very low and they are negligible.
Thank you. I was wondering, actually, you know what, the first thing that I thought about was, because I'm always thinking about food, was the droplets and how you can in a molecular kitchen make all of your droplets the same size. But this is probably not the most useful application for it. But I immediately thought of that. But then I was wondering, when you can make those tiny droplets, and you're using them for printing, you probably can do super fancy tiny 3D printing stuff as well with it.
Yes, actually. Okay, so there are many things you can do really. Like there is 3D printing, though there are some other techniques, because generally 3D printing may be based on a very large solid content. So you may need like structures that are very, very tough and solid in that sense. So it may be that the viscosity of your inks may be a bit too high for Inject itself. So you may go for something a bit more similar to extrusion and those things. However, that said, there are combinations. So Inject is used in certain techniques in 3D printing in which you have a bed of powder that cross-links with certain chemicals. So you basically shoot the chemical to cross-link what you need, and then you just remove the other powder, right? So again, it's a lovely combination to create that that 3D shape. It's not exactly just shooting the drops, and there are things in which you can do that. There's even reactive printing in which you have, imagine, two print heads. One of them prints one very low viscosity chemical, and then the other one prints just behind that and on top another low viscous ink that reacts with the first one and solidifies or jellifies. So I mean, again, it's, yeah, those, I mean, there's a myriad of things you can do with that. I think that was, yeah. And the, oh yeah, I wanted to mention on the alginate. So it's interesting because you know that's very, well, it's used in kitchen, actually in the kitchen. And basically now it seems there is a bit of a trend about explaining chemistry and physics like in the kitchen. So there are, I've seen like online courses and things like that, like, you know, the physics of the kitchen or the chemistry of in the kitchen, right? And you know, it's there. I haven't managed to look into their content, but I guess, you know, there are so many things going on in the kitchen that definitely it would apply there. And actually alginate again is used for these kind of gels, like, you know, in a bigger scale, but yeah, that's something.
So it's not just the greedy me.
No.
That's very good.
It's, yeah,
cool.
It's something that is going on. It's very trendy. You're very trendy, Eva.
I'm just hungry all the time. Yeah, and then I wanted to ask. So your viscosity apparently it plays a very big role if you can do that or not. And then there are those kind of materials which are solid but not really, like glass. I don't know, which is a very, very slow liquid apparently, or something in between, as a completely non-engineer physicist.
No, let me share this again with you. Am I sharing the screen? Yep. Am I sharing, Eva?
Yeah, you are.
Yeah, okay, great. So I was going to say, basically what you're defining is something like this shear thinning behavior, in which sometimes, I mean, it could be, but again, you don't have like a constant viscosity. You may have, again, like a large viscosity when it's slowly flowing. This is basically what means kind of, you know, like the flow is quite slow somewhere here, it's quite large somewhere here. So again, you have a large viscosity to start with, but then if it flows faster, or if you apply kind of more like a stress to it, then you can just, like, the viscosity can drop. So that's one thing. Generally, the inks are shear thinning because, again, you want, I mean, when you squeeze them through a nozzle, so a nozzle would be a contraction, you want them to, again, to lower their viscosity. So you formulate the ink so that it tends to do that. And then there is another thing. Generally, not with all inks, but you tend to increase the temperature a bit. So you may not be working with room temperature. You may be increasing the temperature of the ink. Could be 40 degrees. It doesn't have to be very, very high. But that means that also the viscosity is a function of the temperature. So increasing the temperature tends to generally decrease the viscosity. So you both work with, again, that sort of behavior of a slow or fast flow, and again the temperature. And actually there is something else here, dynamic shear flow, for instance. This defines two different coefficients. one of them gives you the elasticity of the fluid, and the other one the kind of viscosity of the fluid, like that sort of easy or non-easy to flow measurement. And actually this is frequency basically. So you're imposing, when measuring this, you're imposing like a lower or a larger frequency. So you're vibrating the liquid, and basically what you're trying to assess is, you know, like that sort of a slow motion when you vibrate it very, very slowly, or, you know, like very flowing motion when you go for, that's if it's a shear thinning one. It could be the other way around, that you make it vibrate more and it just becomes more elastic, more solid.
This is so complex. Do we have more questions from somebody from the audience, maybe? As you see, I'm also asking really stupid questions because I don't understand half of those things.
No, those are great, because again,
so please, even if you feel like, you know, something you would like to have something clarified, or just have a really wild question, that's fine too. Nope, everything clear. Okay.
I would have gone for talking more if I had known.
Ah, there we go. How did you get into engineering and then inkjet printing especially?
So basically engineering, I always liked it, just because, well, actually I wanted to go for physics, I must admit that. But, you know, I found like engineering was kind of, you know, applying all physical concepts, maybe closer to the real world, like manufacturing processes and things like that. So I went for engineering in the university. And then again, my thesis was about that sort of instability in those liquid jets. So that at some point took me to kind of inject printing, because it's also about those free surface flows I was mentioning and those instabilities. So basically it seemed like a natural kind of step into it. And interestingly, I got into a PhD related to fluid mechanics, because I found fluid mechanics particularly challenging when I was studying engineering, and I am a bit stubborn. So I tend to say like, oh dear, I find this really, really challenging and really difficult and really beautiful at the same time, just because it's super difficult. So I tend to then go for it. I may just, you know, I like problems, I suppose. So yeah, I ended up saying, okay, maybe I should learn more about this that I don't understand too well. I won't understand it too well, even in years to come, but you know, I understand it a bit better than I did before.
Yeah, thank you. That's a really nice answer. It's a really nice approach, because how are you getting better if you're not getting into stuff you don't know yet? Would be boring. Exactly. That's very good. Okay, I don't think there are more questions, so maybe we can actually finish in time once. And yeah, thanks so much for your talk again. It was fascinating, and I have to ask you a load of questions. I already know, because we're also like, we're, you know, working in a lab, we have those dispension systems for little protoplasts, for little cells that are supposed to dispense single cells, or I would like to have one for seeds, because putting out seeds is a pain, one by one. So I have to chat to you anyway. Thanks everybody for joining, and yeah, we hope to see you again for our next talk. And yeah,
thank you, Eva. And one last thing, thank you, Ela, because of organizing all this. So she is our development officer, so behind this. So thank you so much for helping us with all the organization and all that.
Absolutely, that's true. Okay, cool. Thanks everybody. Bye bye.